Okay, we're on the air, right? So here's the schedule. The final exam, Tuesday, December 9th, 4 to 6:30 in GCS 118. And if anybody has a problem with that, let me know. And let's see, homework 6 is due today, and so I'll grade them and have them back on Tuesday. Thursday's Thanksgiving. Happy Thanksgiving. And then we have only 2 more classes, next Tuesday, next Thursday, and then that's the end of the semester, except for the final exam. So on Tuesday I'll go back over homework 6, not that there's that much to do on it. I think it was straightforward, so everybody should have done that with no problem, and the point there is to appreciate what it's all about. And the homework that I had originally assigned, homework number 5, which I didn't give a date and I skipped, that's the central limit theorem. I'm going to go over that in class, so make believe it's a homework assignment, but you don't have to run it and hand it in. I would suggest that you run it and do it because you're responsible for that material. There could be something on the final, but I'm not going to grade it because that would take a week. We don't have a week. So I'll discuss that in class on Tuesday, and then Tuesday and Thursday will just be central limit theorem and whatever questions you have studying for the final. So are there any questions at this point? So I want to do 2 things today. Actually 3 things, I guess. Let me do homework number 4, the part 3, the part that was the only part that I hadn't done in class. And then let me finish up with the queuing problem. And then I want to do the course evaluation. So I hope I have time for everything. So first of all, homework number 4, case 3. So let's see. I'll do that here. So this is homework 4, and we're going to do case 3. And in case 3, what you're given is you're given a density function, which is 0 when t is negative, 2 minus 2t when t lies between 0 and 1, and 0 when t is greater than 1. And if you draw a graph of that, it looks like this. Here's that little f. There's t. Here's the value 0. Here's 1. So that's 1. That's 2. And so if you draw that graph, it would look like this. A triangle. And of course, its area is 1. Area of every density function has to be 1. So one of the things you have to do is you're going to have to generate random variables from this population in a simulation, which means you have to use the inverse transform method. So you have to find the distribution function of x. And remember, by definition, that's the area to the left of t under the density function. In other words, you imagine that you have a curve down here, capital F, whose height represents the cumulative area to the left of t of the graph above it. And of course, this one is a derivative of that one. So if you plug this formula in here, then you'll see that what you get is the integral from 0 to t of 2 times 1 minus u du. In other words, I'm going to factor out the 2 here, and remember the dummy variable is u because I'm already using a t in the upper limit. So that thing goes in there, and now I just integrate. Now, of course, this presumes that the t that I'm talking about is between 0 and 1. So for t lying between 0 and 1, then this would be the formula. Okay, so I now have to integrate that, but integrating that is very simple because you can see immediately that when that integrates, I get 1 minus u quantity squared. In other words, the derivative of this is that. and I evaluate that between 0 and t. And then I plug in a t and 0, and I get 1 minus t quantity squared. Okay? So you integrate that, you get that, then you plug in the t to 0, and you subtract, and you get that. Very simple. So if you draw the graph of this thing right here, it will look like this. Here's the value 1. Here's 0. Capital F is 0 and t is negative. Then when you plot that, you see that when t is equal to 0, this has the value 0, and then it increases parabolically like that until you reach the value 1, and then it stays there. So for any t, the height of this curve is the area to the left of this curve at that point. And of course, this curve is the derivative of this curve. So now in order to get the equation that generates the values whose distribution function is this, you take the value of the random number, you put it on the vertical axis, project over to the curve and down, and you would call that x. So that means algebraically what you're doing is you're setting the value r equal to the value of this function, which is this, except that now t is called x. So this is 1 minus x quantity squared. So you want to solve that for x. So that's simple enough, because all I do is bring this on the left-hand side, the r on the other side, and then take square roots. And so this implies that x is equal to 1 minus the square root of 1 minus r. Okay, so I just solved this equation right here backwards to get x as a function of r, and that's the answer. Which means that in terms of code, at least in BASIC, the way I would write this would be x equals 1 minus SQR, that's square root in BASIC, or I could raise it to the 1/2 power of 1 minus a random number. So that'll do it. Okay? Any questions about that? Now, you want to worry about y, which is the sum of x1 plus x2. And the x that I wrote over here, that's actually x2. So to calculate the expected value of y, you use the theorem that says that the expected value of the sum is the sum of the expected values. So this is the expected value of x1 plus the expected value of x2. The expected value of x1 you already had from a previous homework, and in fact you had to do that for case 1, and that's equal to 1/2. And it's easy to calculate the expected value of x2. I think it turned out to be, what was it, 2/3 or 1/3? Anybody remember? 1/3. Was it 1/3? So that would be 3/6 plus 2/6 is 5/6, and 5/6 is the answer I have in front of it. Okay, so I'm not going to work out the details of calculating this expected value and showing it's 1/3. Everybody should be able to do that. Then you had to calculate the variance. And that's the sum of the variances. Now, you already calculated the variance of case number 1. It was 1/12. And so now you calculate the variance for the second one, same kind of thing. It turned out to be, what was it, 1/18th? Is that right, 1/18th? Yeah. So this is 336 plus 236 is 536. So that's the variance. Again, I'm not going to bother to work this out, but this should be straightforward. If anybody has a problem with this, come and see me after class. Should be easy. So the hard part was calculating the convolution. So everybody okay up to this point? That means yes, right? Okay. So here's the convolution. First of all, we have the formula. So let's call it f sub y of t. And the formula is that this is an integral from minus to plus infinity of the density function of one of them evaluated at u times the density function of the other one evaluated at t minus u du. And of course I could have written x2 here and x1 here, but I chose to write x1 here because it seems to me that that's simpler. Because the next step, remember that this is the density function for the uniform, and this function is 0 if u is not between 0 and 1, and it's 1 if u is between 0 and 1. So that means I can immediately rewrite this as the integral from 0 to 1, because outside of that this function is 0. Inside it has the value 1, and then I have the density function of x2 evaluated at t minus u du. This is exactly the same thing you did in homework 0, and in fact in this homework in case 1, except that in case 1 this f was the same as that f, and now in this case this f is different. This f is given by this thing right here. That's the only difference. Okay, so now you do exactly what you did in case 1 and in homework 0, which is to make the substitution. So what you say here is let, for example, y be equal to t minus u. When you do that, you get the integral of the density function of x2 evaluated at y dy evaluated between t minus 1 and t. So this step is exactly what you did in part 1. So that's why I'm not going to do it here. It's exactly the same thing. The only difference is that in that case, the function here was 1. It was a different function, that's all. But the limits are exactly the same. The way you make the substitution is exactly the same. So this is step-by-step analogous to what you did in case 1 for the uniform. Okay, now you've got to evaluate this thing. And so one case, the first case, well, there are actually 4 cases, but 2 of them are trivial because in those cases everything is 0. So suppose that t lies between 0 and 1. So then you would have that the density function of y evaluated at t, this guy right here, is given by whatever one I get when I evaluate that. Now, since t is going to lie between 0 and 1, that means that the lower limit would be 0 and the upper limit would be t. Because this function in here, when y is not between 0 and 1, is 0. So I want the t minus 1 and t to include only the values of y between 0 and 1. So if y lies between 0 and 1, then this is a negative value. This value would be t between 0 and 1. So this integral would run from 0 to t. Exactly the same as in the previous case, as in case number 1. So still there's no difference. But now what goes inside is 2 times 1 minus y dy, as opposed to 1. Because in the previous case, where this f was uniform, that function is 1, and now that function is 2 times, or 2 minus, if I'm talking about y as a variable, it will be 2 minus 2y. With the 2 factored out, it's 2 times 1 minus y. I wrote it that way just like I did here, because that makes it easier to integrate. So now I integrate that, and when I integrate that, I'm going to get minus 1 minus y, quantity squared, between 0 and t. That is, if I differentiate that, I get that. So this is easy to integrate. And now I plug in the t, I plug in the 0, I subtract, and that gives me this answer. It's 1 minus t, quantity squared, which is the same thing if I expand it as 2t minus t squared. So that's what little f is, 2t minus t squared, when t lies between 0 and 1. Now, when t lies between 1 and 2, again, it's exactly analogous to what was done in case 1. So now we have the density function is the integral. The integrand is the same, 2 times 1 minus y dy. But now, since t lies between 1 and 2, the only place where this function is not 0 now is between t minus 1 and 1. Again, it's exactly the same as what was done in the previous problem. So the limits change, but the integrand remains the same. And that gives me, of course, the same thing to evaluate. So in other words, I'm still left with minus 1 minus y squared. But now the limits are between t minus 1 and 1. So I plug in the 1, I plug in the t minus 1, I subtract, and the answer turns out to be equal to 2 minus t quantity squared. And if I expand that, I get t to the 4th minus 4t plus 4. And of course, for t less than 0 or greater than 1, the answer is 0. So let me erase this above here. And write this out. Okay, so now the density function of the sum is equal to 0 if t is negative. It's equal to 2t minus t squared if t lies between 0 and 1. It's equal to t to the 4th minus 4t plus 4 if t lies between 1 and 2, and it's equal to 0 if t is greater than 2. So you could draw the graph of that. So here's t. Here is the density function of y evaluated at t. Density function of y evaluated at t. And here's 0, here's 1, here's 2. And of course, the density function is going to be non-zero only between 0 and 2, because the sum of two numbers that lie between 0 and 1 must lie between 0 and 2. So when I draw the graph of this, I get this branch is 0. Then this branch right here will look exactly like that. That's the value 1. And this branch, if I were to plot it, would look like that. And then I have 0 again. Which is not necessary to plot it, but it's always helpful because, at least for me, it's always good to see a picture. So in the case of where I'm adding two uniforms, this was a triangle, a straight line here and a straight line here. But since now one of them is uniform and one of them is not, and tends to be more towards the 0 side, that takes this distribution function and shifts it, so it distorts it from this triangle. So it's not surprising that it looks that way. And now the question is to find the probability. Let's see, I'll put that here.
Sure.
Question?
Yeah. Could you just say why does t go from 1 to 2? Between 1 and 2.
What you're trying to evaluate is this integral right here. Now, if t happens to lie between 1 and 2, then that means that this thing, if t were 1, for example, that would be 0, and that would be 1. If t is greater than 1, then this is positive, and this is greater than 1. But it's only when y is between 0 and 1 that this integrand is not 0, because the integrand, this density function right here, is given by this, which is non-zero only when its argument is between 0 and 1. This is exactly the same thing as we had in the other problem. So in fact, if I were doing part number 1, which I did in detail in class, which is the case of two uniforms, this statement is exactly the same, and this statement and this statement are the same, except inside the integral, instead of having this function, I would have the other function, which was simply the constant 1. So the only place they differ is in what's in this integrand here, which would be 1 in case 1, and is this in case 3. So it's step by step, it's exactly the same thing. The limits are the same. The only thing that changes is what fits inside of here, and of course that affects the answer. But it's still going to give you values that lie between 0 and 1 and 1 and 2. Now, from an intuitive point of view, why should the values, the non-zero values, lie between 0 and 2? Well, what you're doing is you're adding up two random variables. One is uniform, which always takes values between 0 and 1. The other has this density function, which always takes values between 0 and 1. So if I'm adding two things that always take values between 0 and 1, the sum has to take values between 0 and 2. So outside of the range between 0 and 2, you would expect the density function to be 0. And you know that you would have to have a non-zero function between 0 and 2, because otherwise it wouldn't make any sense, because remember, you're adding up two random variables which lie between 0 and 1, so their sum could lie between 1 and 2. The maximum value could be is 2, the minimum value could be is 0. Yeah?
Question on the density function between 1 and 2. Why is it t to the fourth and not t to the second when you expand
Here?
it out?
I don't know. Good question. It's because I copied wrong. Good observation. Right?
Right.
Okay. I'm just squaring that.
Right.
So that was just a mistake. A thinko, as they say. I'm better off if I actually think about it and do it rather than copy things. I'm not good at copying.
It's easy to make up.
Yeah, right.
Typographical.
Okay, so that should be a square. Okay, so this is a parabola and that's a parabola. And in fact, these two curves are the same. If you flip one over and flip it again, that and that would lie on top of each other.
Yeah, the top one, Charles.
Okay?
On the upper left-hand corner.
If you took this one and flipped it that way, it would look just like that. And if you flipped it back, it would lie right on top of there.
Right. What they're talking about is on the right-hand board, the upper left, where you got the four cases of alpha y.
Ah, yes, okay.
And then there's another
Right.
t squared up there.
Right. My mistake is carried through. And of course, you would expect that the density function would be continuous intuitively, and that's true. All you have to do is plug in the value 1 here and 1 here, and you see that they both give you the value 1 here. And when you plug in 0, you get 0, which is what you would expect. And when you plug in 2 in here, you would get 0. So all of these things should make sense. That is, you should always, whenever you do these kind of problems, you should always think, does your answer make sense? In this case, it should agree with simulation. That's part of making sense. But also, you should have a function that looks reasonable. And of course, the total area has to be 1. If it isn't, then there must be a mistake. So, step by step, this is almost identical with what you did in case 1. The only difference is in case 1, this function here was a constant between 0 and 1, whereas now it's given by that formula between 0 and 1. But everything else is the same. Okay, so now you have to find the probability. So I'll do that here. I'm going to erase this. And we want to calculate the probability that y, the sum of the two random variables, lies between 0.25 and 1.35. So that means I want to integrate between 0.25 and 1.35 the density function of y. Also, lots of people, I get tired of taking points off of this, so I just ignore it now, but I really shouldn't. People leave out parentheses and they leave out the dy. You should write everything down so it's correct, because remember, you should take the view that this is like writing a program. If you write a program and you define things and then you're not consistent from step to step, or you leave out parentheses or things like that, it's not going to work. Well, this thing isn't going to work either unless you actually ignore what you wrote. And the reason that people run into problems is because in a freshman kind of class, you never have the problem of having a distinction between the variable of integration and another variable. But if you ignore that distinction, then you don't get the right answer. And people ignore the distinction because they don't use the notation properly. If you use notation properly, it just leads you along. It's hard to make a mistake. In fact, that's what a computer does. As long as you give it the right notation, as long as you follow the rules and press the button, it does what it's supposed to do. It's only when you don't follow the rules that it's not going to work. Okay, so you follow the rules like you're supposed to do in life, and that means find this area between 0.25 and 1.35. So that's this area right here. But if you're going to integrate it, you have to recognize that it's got to be broken down into two pieces because there's a different formula for f between 0 and 1 and between 1 and 2. So that means that this is going to be the integral from 0.25 to 1 of the formula for that piece, which is 2t minus t squared dt, plus the area between 1 and 1.35. And in that range, the formula is t squared minus 4t plus 4 dt. Now, those are simple integrals. You can do them by hand, or you can do them with a calculator. And when you plug in those numbers, what you get is exactly 0.851167. And that's the story. When you run the simulation, of course, you get a value very close, which is supposed to tell you that it all makes sense. And part of the point here is that students have a tendency to look at certain kinds of math problems as being independent of reality. They're just some manipulation you make. You get the right answer or the wrong answer. You look it up in the back of the book and you move on, and who cares? But this shows you that this stuff, which may look abstract, it actually has meaning, and all the steps in the derivation have meaning. And it produces for you things that are physically meaningful. Because when you actually conduct the probability experiment, you will find that if you take the two random variable values, add them up, and ask for the fraction of them that fall in this range, it will be this number. Okay? So that's all there is to it. So, any questions about that? On a final exam, I'm not going to ask you to do a convolution. So don't worry about that part, right? It seems to be the stumbling block in the course. But in part, this is a theory course, a math course, and if I didn't do that, there wouldn't be any math in the course. It's too simple. So that's basically the only mathematics there is in this course, except for really stuff you already know. Okay, so that's homework 4. So everybody okay on that? Okay, homework 5, remember, I'm not requiring you to hand in. I'll do it in class on Tuesday. And now I just want to finish the discussion of homework 6, which of course came before homework 5, which is in our tradition because homework 1 came before homework 0. So we have to maintain that tradition of doing things out of order. Yeah?
I'm still not comfortable with why 9 to 1 and 2, but I don't know if you prefer to explain after class.
Say that again?
I'm still not comfortable with why you did it between 1 and 2. The T between 1 and 2. But if you want, you could explain it after class. That's fine.
I have this integral. Let me go back. We saw that the density function, after we simplified, was the integral between t minus 1 and t of the density function, the density function of x2 evaluated at t minus u. Is that right? Let me look back and where I was here. Yeah. No, excuse me. It was y. You'd already made these substitutions. y dy. So this says we want to take the density function of x2. Here it is. So here is f x2, and let's call the variable y. So that's y. And it would look like this. This formula here is 2 minus 2y. That's 2. This is 1. This is 0. And the function is 0 here and 0 there. So we want to find the area under this curve between t minus 1 and t. Well, that depends on where t is. If t is here, then t minus 1 is here. Right? This is a window of width 1, and the area under this curve between here and here is 0. Okay, so that's this branch right here. Suppose that t lies between 0 and 1. So there's t. That means that t minus 1 is over there. I'll erase that. Okay, now we want to evaluate the area under this curve between there and there. But between t minus 1 and 0, this function is 0. So therefore, what we have is the integral from 0 to t of that. In fact, I don't even need to integrate with calculus because I could find this by geometry. Okay, the area between here and here is exactly given by this. I could find that by simply finding the area of this triangle and subtracting it from the area of the whole triangle, which is 1. So this thing is this area. Okay, now here's 2. Suppose t lies between 1 and 2. If t lies between 1 and 2, then t minus 1 lies between 0 and 1. So now the graph looks like this. Here's t minus 1. So now I want to find the area between t minus 1 and t. There's t minus 1. That's that area right there. Because between 1 and t, this area is 0 because the graph is 0. So this becomes the integral from t minus 1 to 1 of this function, and that gives me this. That's in fact this triangle right here. So this is exactly the same thing we did before, except that before the function that we were evaluating, whose area we were evaluating in the window of width 1 between t minus 1 and t, was a constant. This is in case 1. In case 1, the function looked like this instead of like that. But everything else about the argument was the same.
The question I was asking is, why did you say 2? Because I didn't see anything in the function to basically suggest that I should evaluate to 2.
Well, because this is the function that I'm trying to evaluate. So I'm trying to find the area. Let me draw this again. Okay, here's fy of t. I'm trying to find the area under this triangle between t minus 1 and t. And that's 0 and that's 1. Now, between t minus 1 and t, that's a window of width 1. But where that window lies depends on the value of t. So I can imagine I have this window which is moving across here like this. Now, if t lies between 0 and 1, then I'm including some positive area. If t minus 1 lies between 0 and 1, then I'm including positive area. But if t minus 1 is greater than 1, which means t is greater than 2, I'm including 0. And if t is less than 0, I'm including 0. So as I move this window across, I have two branches. One is where the t lies between 0 and 1, and the other is where the t minus 1 lies between 0 and 1. And that was the same argument no matter what the shape of this thing is. The only thing that affected it was the fact that it was non-zero between 0 and 1 and 0 everywhere else. So I could have given you any function at all that fits in here. It doesn't make any difference what it might be, as long as it was defined between 0 and 1, and the answer would be exactly the same, except that, of course, when I evaluated the integral, I'd get a different answer because I'd have a different integram. But the limits would be the same. Everything else would be the same. Okay? Everybody okay on that now? Okay, so let's get back to the queuing problem. So let me ask you, this was straightforward, everything worked out, is that correct? Nobody should have had any problem with it. So the interesting thing about this, is that right? I'm hoping. Everybody's so non-committal. So what this shows is that the simulation is surprisingly simple and describes what appears to be a very complicated probability problem. And the other fact is that even though it's a complicated probability problem, there still are some simple formulas for it, which is sort of surprising. And if this kind of problem interests you, then you should take the queuing theory course next semester. And it's remember, it's given as under two numbers. There's a graduate number, the undergraduate number. Let's see, what do we have? It's MAP 4260, that's the undergraduate version. MAP 6264, that's the graduate version. And both classes will attend the same lectures, which are feeds lectures, but the homework assignments will be slightly different or graded differently to make a difference between graduate and undergraduate. And the structure of the course will be sort of like this one in that we'll go through these arguments, trying to understand things intuitively and mathematically. That's the theory. And then there'll be a simulation, just like this homework problem. And what you'll do is you'll compare the theory with the simulation, and hopefully everything will agree. And then little by little, you build the models up in a systematic way. But it's not a boring way. It's systematic based on physical insight. It's not just a matter of going from t squared to t cubed or something like that. And then hopefully what you get is a feeling for things. So now I want to test whether or not you have a feeling. So what I said was, let's compare FIFO, which is what we simulated, and LIFO. And what I want to calculate is the expected value of the waiting time under FIFO and compare it with the expected value of the waiting time under LIFO. Now, FIFO, what happens is, this is a queue. So when someone arrives and there's customers in front of him, he joins the end of the queue, so he doesn't get served until everyone in front of him gets served. LIFO is the reverse. LIFO is a stack. So now, when somebody arrives, he immediately enters service, but if he doesn't finish service before the next guy arrives, he gets pushed back, and the new arrival takes his place. So this might have some advantages over this, or might not. The advantage here might be that if a customer arrives and his service time is short, then he doesn't have to wait, because he immediately enters service, and he's not likely to be interrupted, so that means that he gets his service independent of the number of people who arrived in front of him. He's only affected by the people who arrived after him. On the other hand, he could suffer, because if he gets interrupted, then he goes back in the queue, and the guy in front of him who just interrupted him could also get interrupted, and he goes back in the queue another step. And so what it means is that customers whose service requirement is short will do better in this case, and customers whose service requirement is long will do worse in this case. But what about the average over the whole population? So what are the possibilities? One is that FIFO is better. In other words, the expected value of the waiting time in FIFO is less than in LIFO. And another is that it's worse. And another is that they're the same, because even though some guys do better here, some guys do better here, and since the total amount of work done by the server is the same, all he's doing is mixing up the order of the customers, then everything balances out, so on average it doesn't matter. And so I put these down last time, and I asked you to, did I ask you to vote? Okay. But then I said, well, what's going to happen? I guess I was getting ahead of myself here. So let me just vote on these. Let's do that first. How many people think that overall, on average, FIFO gives me a smaller waiting time than LIFO? In other words, FIFO is better. Looks like 5. How many people think LIFO is better? Looks like 2. How many people think that they balance out? Let's say 4. Okay, so now, Monty Hall style, let me introduce another possibility, which is that it depends. That is, you can't say that no matter what, this is better or worse or equal, but maybe there's some other element that affects the answer. For example, it might depend on the utilization of the server. So with that information, maybe, which is similar to the earn problem we had. Remember, the question was, is the probability of red bigger, smaller, or the same, or does it depend on the composition of the earn? And in that case, the answer was, it's always the same no matter what. It doesn't depend on the composition of the earn. That was what confused people at the beginning of the course. So this purpose of this is to confuse you at the end of the course. So let me say depends, and give you a chance to pick another curtain. Okay, now how many people favor FIFO as being better? What was that? Where? You're voting again. How many people favor now, the new vote, favor FIFO as being better? Okay, so it was 5, now it's 1. You got one guy sticking to his guns. How about people think LIFO is better? Okay, looks like we got 4. So now we have a strange shift. How many people think it depends? All right, looks like we got about 6. I'm estimating here. Oh, wait a minute. Equals. That's what we were looking at. Equals. We got 1, 2. Okay. How many people now think it depends? Okay. So now we got, let's say, 5 there. Looks like we got more votes now. Anyhow, let's see what the answer is. Okay, so now I'm going to give the answer. So we already have a formula for FIFO. The expected value of the waiting time for FIFO, that's the Polytechnic formula. That's rho over 2 times 1 minus rho times the average service time divided by 2 divided by 1 plus the variance of the service times divided by the square of the average service time. That's the Polytechnic formula. That's what you used in homework 6.
I thought it was just 1 minus rho.
Rho over 2 times 1 minus rho.
You have 1 minus rho. Yeah.
Okay. Okay, that would screw everything up. Okay, now this you don't know, but now I'm going to give you a formula for the expected value of the waiting time under LIFO. And that's equal to rho over 1 minus rho E of x. Let me make sure I remembered that right. Yep, that's what I got. Okay, so this formula I didn't derive in class. I didn't derive this one either. I'm just giving you 2 different formulas. Now, if you look at these formulas, you'll see something remarkable about it, which is that this formula doesn't have a variance in it, and this one does. So they're going to differ depending on the variability of the service times. In other words, the answer is depends. Now, if you draw a graph, here's what I'm going to do. I'm going to plot the average waiting time in the 2 cases as a function of the variance of the service times. So let's look at the case of LIFO. The answer doesn't depend on the variance of the service times. So in fact, it's constant. So I can change the variance. I can make it more variable, less variable. It doesn't make any difference. The average waiting time depends only on the average service time and on the utilization of the server. So here is the value rho over 1 minus rho times the average service time. Okay, now what about this one? Well, this one depends on the variance. Suppose the variance is 0. In other words, suppose I have constant service time. If the variance is 0, then this multiplying factor is 1, and this formula is exactly the same as this except for the 2. So in other words, it's half as large as this. So here is the value, which is 1/2 of rho times 1 minus rho E of x. So if the surface times are constant, then the LIFO is better because, then FIFO is better because that's FIFO and that's LIFO. So in fact, I would wait half as long under FIFO as I would under LIFO if the variance is 0, which means if the surface times are constant. But suppose the variance is not 0. As the variance increases, this value right here increases linearly with V. So if I were to graph it, I would get a straight line. So this is the average waiting time under FIFO, and this is the average waiting time under LIFO. And there's a crossover point. And it's easy to see that the crossover point occurs exactly when the variance, the ratio of the variance to the square of the mean is 1. Because when that's 1, that thing is a 2, that cancels out that 2, and that gives me exactly the same value as this. So this crossover point is where the variance is equal to the square of the average surface time. And what is that? Whenever I have exponential surface times, okay, if x is exponential, then the variance of x is equal to the square of the average of x, as we've already seen. That's always true no matter what the number is. So what does this tell you? It tells you that if the surface times are less variable than exponential surface times, then this curve gives you a lower average waiting time, which is FIFO. But if the surface times are more variable than the exponential case, then this curve gives you the lower, and that's LIFO. So the answer is, it depends, and it depends on the variance of the surface times. If the surface times tend to have a low variability, close to constant, then FIFO is better. If the surface times have a high variability, more variable than total randomness, which is the exponential, then LIFO is better. So that illustrates an important point about this kind of subject, which is these formulas don't simply give you numbers, they give you insight. And so a person who is designing such a system and wants to choose between a queue and a stack would consider as part of his input, part of the factor on which he would make a decision is how variable is the bandwidth requirement, is the surface requirement. If you think that it's highly variable, then what you want to do is you want to choose LIFO, a stack. But if you think that it tends to be constant, doesn't vary very much, then you want to choose FIFO. That's exactly what the formula tells you. And if the surface times are exponential, then it doesn't matter because you get the same result in both cases. So, for example, a typical problem in the queuing course would be, well, we have to derive these things and derive this, but then the question is, well, how does this work? Does it really work? And so what you would do is you would write a simulation for a stack, compare the simulation values with a simulation for a queue, and presumably you would get these two curves. And that would convince you that this is correct. Okay? Okay, so this is all supposed to be very exciting and impressive. Any questions about this? Questions about anything? Okay, so I'm hoping that at the end this all sort of hangs together, even though you realize that you don't know enough at the moment to derive these formulas, but if you took the queuing theory course, then you would. Okay, so what I want to do now is hand out these course evaluation forms. We've got about 20 minutes. And there's two sets. This is the important one, though. This is the university one, and then there's the departmental one for our ABET accreditation. So I need someone who will volunteer to do this. I got to wait outside and sign the thing. Anybody want to volunteer? Okay, it has to be brought back to the secretary in computer science this afternoon, because this is the last bit.
On the floor there, right next to your office.
Yeah, 300 or 400 upstairs. If you leave it in 300, different. Okay, so I guess we don't need the TV anymore. You want to be on TV?
No, not really.